All right, let's talk about the Haber process. It's a application of Le Chatelier's principle. It's used for the commercial production of ammonia. And we produce a lot of ammonia this way, and we end up producing a lot of fertilizer as a result. So here's the basic process where we have an inlet for our N2 and our H2, and we run that across a heat exchanger and a catalyst and a heating coil, and we allow that to produce ammonia. But it's an equilibrium. Some of it's still going to be H2 and N2. So we pass that through to the other side where there is a cooling coil. We allow that to condense and form liquid ammonia. So we're definitely not at room temperature over here. We have to cool that to get the ammonia to liquefy. But any uncombined N2 and H2 should be pumped back through the system and allowed to continue to react. But we keep shifting the reaction towards products by removing the ammonia. So we're removing a product, allowing the equilibrium to continue to shift towards products. So it is a practical application of the Le Chatelier's principle process. So if we look at an example of shifting equilibrium, let's say we got a 2-liter vessel which contains the following things at equilibrium. So these are equilibrium amounts of moles. So 1.20 moles of COCl2, 0.6 moles of carbon monoxide, and 0.2 moles of chlorine. We're going to calculate the equilibrium constant based on that. Now, part B is, once we have that equilibrium constant figured out, if I add a little bit of Cl2, how is it going to shift? And so we know that adding a reactant of Cl2 will cause it to shift towards products, but how much? We're going to do it a little bit more numerically than we have before. So let's go to the paper and actually figure that out. So if we look, I've already got the reaction written out, the volume. And so if these are the moles, if I'm dividing by 2, the concentrations will be half that much. So it'll be 0.30 molar, 0.10 molar, and 0.60 molar. So what's our equilibrium constant? Our Kc is going to be concentration of COCl2 over the concentration of CO and the concentration of Cl2. Now we just plug and chug. 0.60 molar divided by 0.30 molar and 0.10 molar and get our equilibrium constant. So we're going to run that through our calculator. 0.6 divided by 0.3 and 0.1. And so we're going to get 20, and we'll consider that as having 2 sig figs because every other number in there does. Now that I know the equilibrium constant, I should be able to predict the shift. So if we still work with our carbon monoxide plus Cl2 going to form an equilibrium with COCl2, all in the gas phase. Now, what are our initial conditions? What's our change? What's our equilibrium? We may need a handy-dandy quadratic equation. We'll just have to wait and see. So, if we know our initial concentrations, 2 of them didn't change, so we're going to say 0.30 molar. And these are all molarities. And this will be 0.60 molar. But now I added 0.8 moles. So 0.2 plus 0.8 would be 1 mole in there, which is going to divide by 2 liters, which will give us 0.50 molar concentration. And so we're going to say 0.50. Now, I know the equilibrium constant, but I don't know how much it's changing, so we're going to use a variable. Since we add the reactant, we know it's going to shift towards product. All the coefficients are 1 to 1, so we're going to say minus x plus x. So 0.30 minus x, 0.50 minus x, and 0.60 molar plus x. So our equilibrium constant Kc, then substituting into this, we're going to say 0.60 plus x divided by 0.30 minus x times 0.50 minus x, and all that's going to have to equal 20. So now I need to do a little bit of algebra. So we're going to say 0.60 plus x is going to equal 20 times 0.30 minus x times 0.50 minus x. Then what we're going to do is combine like terms and FOIL this out. So do a little algebra. 0.60 plus x is equal to 20 times. So then we just need to work the math out. So we're going to say 0.3 times 0.5 is 0.15. And so that's our constant term. And so we get a negative 0.3 and a negative 0.5, or minus 0.80x plus x squared. Then we got to multiply the 20 through there. So 0.60 plus x is going to equal 3. And then 20 times 0.8 is 16, so minus 16x, and then plus 20x squared. So now I've got to combine the like terms, and so we're going to say 20x squared, and then that's going to have to come over, so minus 17x, and then 3 subtracting 0.6 is going to be minus 2.4 equals 0. So then we have to work our friend the quadratic equation. X is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So I need to plug and chug into that. And so b, so that's going to be plus 17 plus or minus, then b squared. So that's going to be a negative 17 squared, but the negative will work out in the square, minus 4 times what? Times a, which is 20, and then c, which is negative 2.4, all divided by 2 times a, which is 20. Simplifying, x is equal to 17 plus or minus. Now let's work out what's in the radical. So we got negative 17 squared minus 4 times 20 times a negative 2.4, and then we're going to square root that. And we get 21.9 divided by 40. All right, so I've copied the simplification of our quadratic equation to another page just for room's sake, because I was getting at the bottom of the page. Subtraction's not going to really work out for us because x needs to be positive before it can go into the equation. So we can do it and say x minus, and so we apply the minus sign. And so you're going to say negative 17 minus 21.9 quantity divided by 40. You get a negative 0.97, we'll say, molar. Now, one, that's out of our range because our biggest concentration in that problem was 0.6, and that number's too big, and it's negative. So we're not interested in that one. Now with the positive, so if I treat it like a positive, so we got negative 17 plus 21.9 divided by 40, we're going to get a positive 0.12 molar. Now that's a number I can work with. So we're going to work with this root and not that root because negative roots are out of the domain. And if it's bigger than 0.6, we're also out of the domain. So copying over from our previous page, our equilibrium concentration of our carbon monoxide was equal to 0.30 minus X. Concentration of our Cl2 was equal to 0.50 minus X. And our concentration of our COCl2 is 0.60 plus X. So now that we know what X is, all we got to do is plug and chug. Or 5. And so that'd be 0.18 molar. This should be 0.38 molar. This will be 0.72 molar. So that would be the equilibrium concentrations of everything in the problem.